Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will solve one numerical and some logical problems in the area of refrigeration. We will start with the numerical. A 10 TR refrigeration system is required for a food storage locker. The evaporator temperature is minus 20 degrees centigrade and the condenser temperature is 50 degrees centigrade. The working fluid is R134A. The refrigerant is superheated by 5 degrees centigrade in the evaporator while coming at the exit of the evaporator. The refrigerant is subcooled by 5 degrees centigrade at the exit of the condenser and before entering the expansion valve. The refrigerant compresses in double cylinder single acting reciprocating compressor having L by D as 1.1. L by D stands for length and diameter ratio of compressor block and 80% of volumetric efficiency. The compressor runs at 1200 RPM. Calculate number 1 mass flow rate of refrigerant kg per minute, bore and stroke of compressor in millimeters and theoretical power required in kilowatts. We will start with the thermophysical properties of refrigerant and we will draw the processes on temperature entropy diagram. Temperature entropy diagram. And the vapor coming from the evaporator is superheated by 5 degrees centigrade. So, state 1 is the saturation state, state 2 is the superheated state. Then the vapor is compressed in a compressor, state 2 to state 3. From state 3 to state 4, desuperheating takes place. Desuperheating of the vapor takes place. 4 to 5, condensation of vapor in a condenser and then subcooling 5 to 6 and 6 to 7 is expansion in expansion valve and then boiling of refrigerant in evaporator from state 7 to state 2 to produce the refrigerating effect. This is the entire cycle. Now, in this cycle, enthalpy of state 1, that is H1. H1 is the enthalpy of saturated vapor at minus 20 degrees centigrade, this is 50 degrees centigrade. So, enthalpy as vapor at minus 20 degrees centigrade, that is 386.55 kilojoules per kg. Enthalpy of state 2 is not known to us, but we know that from state 1 to state 2 there is a sensible heating and the heating temperature difference between state 2 and state 1 is 5 degrees centigrade. So, H2 can be H1 plus Cp delta T. Now, H1 is enthalpy at state 1, that is 386.55. Cp is the specific heat of vapor at state 1, saturated vapor at minus 20 degrees centigrade. This value can be taken from the properties chart. At minus 20 degrees centigrade, specific heat of R134A is 0.816. Delta T is 5 degrees centigrade. That gives the value of enthalpy at state 2 as 390.63 kilojoules per kg. We will note it here. H2 is equal to 390.63 kilojoules per kg. In order to find the compressor work, we need to have the enthalpy at state 3 also. Since it is in a superheated state, we do not have properties of superheated state here, but we have enthalpy at state 4. If we know the temperature at state 3, we can find the enthalpy at state 3 as well. Temperature at state 3 is not known to us. We know one thing, that property at state 2 is equal to property at state 3. So, property sorry, the entropy, not property, entropy at state through 2 is equal to entropy at state 3. So, S2 is equal to S3. Now, S2 we can find as S1 plus Cp natural log T2 by T1. This is a sensible heating process, and during sensible heating the change in entropy can be written like this. Now, S1 again at minus 20 degree centigrade can be taken from here, minus 20 degree centigrade, and entropy of vapor is 1.7413. Specific heat at minus 20 degree centigrade is again 0.816 natural log of T2 by T1. Now, T1 is equal to minus 20 plus 273, that is 253 Kelvin. It is superheated here by 5 degree centigrade. So, T2 is 258 Kelvin. Now, we will be putting here 258 by 253, and this will give us S2 as 1.7573 kilojoules per kg. That is the value of entropy at 2. So, from here we have calculated the entropy at state 2. And how we have calculated? We have taken the entropy at state 1 from the properties chart plus change in entropy Cp natural log T2 by T1. Using this relation, we have calculated the entropy at state 2, and entropy at state 2 is 1.7573 kilojoules per kg. Kelvin. Kelvin. Now, property at this entropy at state 2 is equal to entropy at state 3. So, S3 is equal to S2. So, S3 is equal to 1.7573 kilojoules per kg Kelvin. S4 is, we know the value of S4, that can be taken from the properties of R134A, and S4 is going to be S3 is going to be equal to S4 plus Cp natural log T3 by T4. Now, in this case, T4 is 50 plus 273 is equal to 323 Kelvin. S3 is given here 1.7573. S4 can be taken from here at 50 degree centigrade, entropy at 50 degree centigrade, entropy of saturated vapor is 1.7072 plus specific heat 1.246, natural log T3 by T4 is 323. So, we have taken entropy at this point plus change in entropy while heating from here to here, and we got this expression, and from this expression natural log of T3 by 323 is going to be equal to 0.04037, and from this we find the value of T3 as 336.3 Kelvin. So, T3 is 336.3 Kelvin. Once we have the value of T3, once we have temperature at this state, the Cp T3 minus T4 will give the heat rejected during desuperheating, or we can say that enthalpy at 3 H3 is equal to enthalpy at 4 plus Cp T3 minus T4. Enthalpy at 3 is equal to enthalpy at 4. Enthalpy at 4, it means 50 degree centigrade temperature, enthalpy of saturated vapor, that is 423.44 plus Cp 1.246, T3 is 336.3 minus 323, and this will give the enthalpy at 3 as 440.01 kilojoules per kg. So H3 we will note down here 440.01 kilojoules per kg. Now after H3 we have to find the value of H5. H5 we can directly take from the properties diagram, that is the enthalpy of liquid by enthalpy of R134A at 50 degree centigrade, that is enthalpy of saturated liquid, and this H5 is, we can take from here, it is 271.62 kilojoules per kg. Now once we have the enthalpy at 5, the vapor is subcooled by 5 degree centigrade. So it should come somewhere here, but because this is very close to the saturation line, we can always take this point at here on the saturation curve itself. It is normally taken like this. So the enthalpy at 6 is equal to enthalpy at 5 plus, because there is a subcooling of 5 degree centigrade, Cp delta T. Enthalpy of 5 is, sorry, minus, not minus, it is minus, not plus. So H5 is 271.62 minus Cp of liquid refrigerant at 50 degree centigrade, and Cp of liquid refrigerant at 50 degree centigrade 1.556 into 5, and that will give the value of H6 as 263.8 kilojoules per kg. So H6 is 263.8 kilojoules per kg. Now we have to find the refrigerating effect, because superheating is taking place inside the evaporator. So refrigerating effect will be H2 minus H7. S6 is equal to S7. S6 is equal to S7 because it is an isothalpic expansion process, and that is equal to 390.63 minus 263.8 and is equal to 126.83 kilojoules per kg. In order to find the mass flow rate of refrigerant, the total refrigerating capacity is 10 tons of refrigeration. 10 tons of refrigeration means 10 into 3.5 kilowatts of heat removal rate multiplied by R, that is 126.83, and this will give the mass flow rate as 0.276 kg per second or 16.56 kg per minute. So mass flow rate is 0.276 kg per second or 16.56 kg per minute. Now we have mass flow rate of refrigerant with us. With this mass flow rate of refrigerant, we can always find the power consumed inside the compressor, and with this mass flow rate we can also find the size of the compressor. Now in order to find the dimensions of the cylinder, as we have to find in this numerical, bore and stroke of the compressor. So first of all we will calculate the swept volume of each compressor, that is pi by 4 d square into stroke of the compressor multiplied by RPM divided by 60, that is revolutions per second, that is the total volume handled by the compressor. It is a double cylinder compressor. This is the total volume handled by per compressor per second, meter cube per second, multiplied by volumetric efficiency will give us the actual volume of refrigerant vapor handled by the compressor per second. and that is going to be equal to 0. That is going to be equal to mass flow rate of refrigerant divided by 2, because there are two compressors. So, each compressor is handling half of the refrigerant multiplied by specific volume of vapor. Now, we know the relation between L and D. L by D is equal to 1.1. So, we can always write pi by 4 D square into 1.1 D into 1200 divided by 60. Volumetric efficiency is 0.8. Mass flow rate is 0.76 divided by 2 multiplied by 0.125. And this will give us the D cube as 1.248 into 10 to power minus 3 meter cube, or D as 0.1076 meter, or 107.6 millimeter, or approximately 108 millimeter. So, D is equal to, of each compressor is 108 millimeter. Multiply this D by into 1.1 will give us L. So, length of the stroke is 118.8 millimeter, and that is approximately 119 millimeter. So, length of the stroke is 119 millimeter. Now, the last one is power consumed by the compressor. Power consumed by the compressor is H3 minus H2 multiplied by mass flow rate of refrigerant. Now, H3 is 440.01 minus H2. H2 is 390.63 multiplied by mass flow rate, that is 0.276, and this will give the power consumed by the compressor as 13.63 kilowatt. So, power consumed by the compressor is, here we will write, power is 13.63 kilowatt. Now, we have answers for all parts of this numerical. Now, the same numerical can be solved by using pH diagram. We can also show these processes on pH diagram. Now, in pH diagram, this is minus 20 degree centigrade line and this is 50 degree centigrade line. Vapor is superheated by 5 degree centigrade in evaporator. This is minus 20 degree centigrade constant temperature line. This is minus 10 degree centigrade constant temperature line. So, 15 degree centigrade constant temperature line will lie somewhere here, and if we extend this line, this is the state 2. So, this is state 1 and this one is state 2. Now, after state 2 it is getting compressed and we attain state 3. So, this 50 degree centigrade line, constant pressure line is extended and a line is drawn along the constant entropy line, and we will be getting this point somewhere here, that is state 3, that is state 3. Now, after state 3 desuperheating and state 4 is attained, and after state 4 further condensation of refrigerant in the condenser, state 5, this is state 5. At state 5 the temperature is 50 degree centigrade. Since subcooling is taking place by 5 degree. So, this is a 50 constant temperature 50 degree centigrade line, this is constant temperature 40 degree centigrade line. So, 45 degree centigrade is going to be somewhere here, and this point will shift to 6, here is the point 6. Now, from 6 to 7 expansion takes place, it is a vertical line cutting horizontal minus 20 degree centigrade line, and we will be getting 0.7 somewhere here, this is 0.7. So, we have drawn all the points here. If we take the values from this chart at different states, the values are like this. H2 is equal to 390 kilojoules per kg. H3 is equal to 440 kilojoules per kg. H2 we can take from here, it is 390, H3 is equal to 440 and H6 is equal to 265 kilojoules per kg. Now here, if we take the refrigerating effect is H2 minus H7 and the tonnage is 10 tons of refrigeration. So, mass flow rate is 10 into 3.5 divided by H2 minus H7, that is 390 minus 265, and that is going to be equal to 0.8 kg per second. From the properties chart also we were getting 0.276, and this will give us is equal to 16.8 kg per minute. Work consumed by the compressor W is equal to 0.28 H3 minus H2. So, H3 minus H2 we will take directly from here, 440 minus 390, and this compressor work is coming 14 kilowatt. So, either we solve using this properties table or from pH diagram, we are going to get almost the same values. But this pH diagram is very convenient to use. You can see when we have when we have solved this numerical using temperature entropy diagram, number of iterations were done, number of equations were solved, but here from pH diagram we could directly take the values of enthalpies at different states. Now after the pH diagram, in the area of refrigeration there are certain logical queries, like if we open the door, if we leave the door of a refrigerator open in a room, will the temperature of the room will go down or not? In this case, if in a room is a control volume, if we keep a refrigerator and leave that refrigerator room door open, the room will not get cooled, because here we consider room as a system and there is no heat transfer across the boundary of the room, right? Whatever energy is coming to the room, it is in the form of electrical work, and that electrical work, the energy will increase the temperature of the room. So, in fact, if in this room, if I keep a refrigerator and leave the door of the refrigerator open, the temperature of this room will rise. There are certain other interesting queries also in refrigeration, like a woman informs an engineer that she frequently feels cooler in summer when standing in front of an open refrigerator. The engineer tells her that this is not possible as there is no fan in the refrigerator to blow the cold air over her. So, when you must have also felt when you open the refrigerator door, you feel you get a feeling of low temperature from the refrigerator side. The reason being, when you are standing in front of an open door refrigerator, the temperature inside the refrigerator is low. So, the heat loss from your body in form of conduction and convection heat transfer takes place, and that gives you the feeling of coldness in front of a refrigerator. Now, there is third inquiry, which is the hot water will freeze faster than cold water in a refrigerator. Is it true? Some people conducted the experiment, and what they took hot water in a tray and placed in the refrigerator freezer and noted the time for the ice formation. Then they took the tap water, placed inside the freezer of a refrigerator and noted the ice formation time. Ice formation time for hot water was less than the ice formation time for cold water. So, in this case, actually this is thermodynamically it is not possible. If the temperature is high, definitely more time will be taken by the machine to remove the heat. But what happens when you keep the hot water tray in the freezer? This happens in old refrigerator where defreezing arrangement was not there. So, all the ice which is formed on the evaporator coil gets melted. So, the moment you place the hot water plate inside the freezer, all the ice on the freezer coil gets melted. That is why the refrigerating effect is improved, and the formation of ice is faster. However, in the case when you place the normal water inside the freezer, the this ice layer on the or the frosting on the evaporator coil remains there, and that hampers the heat transfer or the cooling rate, and we get the feeling that the hot temperature water ice is faster than the cold water ice. But this is not thermodynamically, it is, or scientifically it is not possible, and it happens only in the case when there is a no defrosting arrangement, because in the old refrigerator there was no arrangement for defrosting. So, in those refrigerator where defrosting arrangement is not there, this type of elusive effect can be witnessed. Now, I end my lecture here, and from the next lecture we will start with the properties of refrigerants.